Hello, everybody. My name is David Christiansen. I'm a PhD student at the IT University of Copenhagen. I'm kind of on the end of a 4-month internship at Galois in Portland, which was tons of fun. Great place. And what I'm going to be talking about today is type providers in Idris, which are not quite the same as the ones you may have seen in F#, and also how we can use something called error reflection to make our error messages much better. So F# type providers, which I thought were hugely inspirational and great. Here's a screenshot from Visual Studio, and what it shows is the type checker making an HTTP connection to Stack Overflow to get a hold of the actual API that it provides and explore it in real time with auto-completion. This is really, really, really cool. Hugely impressive, you know. Big, powerful, awesome. But when you look behind the curtain, there's maybe a little bit less impressive features than you might expect. And the same goes for template Haskell, which you saw in the last talk. And that's because essentially what you have to do in a system where you can't compute types from values is you have to do code generation. So what these type providers are doing is they're DLLs that are dynamically loaded by the type checker, and they spit out an AST for type declarations and then for code for accessing that. And it's doing it sort of lazily and in real time, which is really cool. But you're still doing code generation, which means that you're not working inside of the abstractions of your language. You know, you can spit out code that's not type correct. You could spit out types that aren't well formed, like you might have spit out a class that inherits from itself. And the type catcher will catch these things, or the type checker will eventually catch these things, but you're not getting any help as an author of a type provider from the type system in this way. And another sort of irritating thing is you've got a bit of a stage restriction, which is that you have to develop these things in a separate module, because if you want to compile something to a DLL so that your type provider, or so your type checker can load it, then it can't be in the thing that's currently being type checked. So what I'm going to look at now is a way that when you have dependent types that you can relax some of these restrictions and do something that may be a little bit more natural for a functional programmer. I'll show how it works inside of a type provider for SQLite, and then look at this error reflection that I've been hinting at for a while. So Idris type providers. First off, what's Idris, for those who don't know? It's a pure, strict functional language, but it's got full dependent types, as opposed to something like Haskell or ML, which does not. It's designed for programming first. Many other systems with dependent types are really sort of designed as proof assistants first and as programming languages second. In Idris, we prioritize things the opposite direction. And the syntax looks a lot like Haskell, but please don't get confused when you see code examples. It's got tactic-based theorem proving, kind of like Coq, but not nearly as good, if you really want that. And it can compile to C, to JavaScript for running in a browser or on Node, and it can also generate LLVM bitcode or Java code. So the key insight behind the way type providers work in Idris is that types are terms like any other, as you saw last night. And because types are terms like any other, we already have mechanism in our language to produce them based on input and output, which is execution. We just run a program, right? So rather than going into a bunch of sort of high-level bullet point stuff, here's some code. This is the type signature for a simple Idris type provider, which is going to read the contents of a file and generate a type based on that. So it's going to take the file name argument as a string, and then it's returning IO of provider of type. And here's the entire code. So what it's doing is it's reading in the file whose file name we specified. It then checks if the string contents of the file, modulo whitespace, are equal to the string int. If so, it returns the type int, otherwise the type nat. And then it's wrapping it up in this constructor called provide, which is a constructor of that provider type, which we'll see a little bit more of in a little bit. Then, if I want to use it, further down in the exact same file, I give this sort of type provider instruction to the compiler. So I say provide the type T1. So T1 is the name that I'm giving to the provided type, and it's going to be a type. We may want to provide other things later. And then we give it the term, which has to have IO of provider of whatever the type is that we've given for the definition that we're providing, in this case type. And then we can say, test is a T1, and it's equal to 3. And 3 here is valid syntax for both an int and a nat, so I'm cheating a little bit. So switching to my favorite operating system, we can see this type provider in action. So this is just the code from the slide with a couple of imports at the top. We can see that it's going to be reading in this file called the type. So if I open up the type, we can see that it's containing the string int. if I load the buffer, I get an Idris REPL, and now I can type test, and we get the int 3. If we come back to this file and call it lint instead of int, load it again, and we get the nat. So what we've done is, at compile time, essentially run unsafe perform IO of this thing, pulled out the result, and stuck it in as the right-hand side of a definition. Types bring safety. Another example of a very safe type provider will come in just a minute to illustrate how errors work. So this provider type that we're seeing here is basically the same thing as either string for the Haskell programmers in the room. The reason why it's a different type here is 1, for readability, and 2, so I can add more constructors in the future to make it do crazier stuff. So the error constructor here is used for the type provider to return an error message to the user that is in some way more interesting than whatever the representation of some exception it might otherwise throw would be. So to see an example of this, let's take a look at an ordinary Idris program. You could use this at any time, and it's intended to keep the young people out of your program. This could be the first thing in your main, for example. And so the code is first, it prints out to the console, how old are you? It reads a line of input, attempts to parse that input as an int. If it fails, then it says didn't understand and tries again. And if it succeeds, then it will return whether or not the int that it parsed is greater than or equal to 18. In other words, if the person at least claims to be an adult. We can stick that in a sort of simple type provider where we say that we first confirm the age of the user, and if they're old enough, we say OK and set up true as the right-hand side of our definition. If not, then we're returning an error saying only adults may compile this program. So let's say we want to keep the whippersnappers out of our type system. So here's the code from the slide, and I load it, and the interpreter pops up, or the compiler pops up and saying, how old are you? And I'm just going to say, like, buzz off. I don't want this. And if it didn't understand me, and it's going to keep doing that for a long time. So now I could say, I'm 12. And I get back this error that only adults may compile the program. And if we take a look at this source location here, we see that it is, in fact, the type provider location. OK, so that's, maybe I actually want to compile my program, so I'll tell the truth. I'm 30. And it says, OK. And my program has type checked. If I go back to Geezer, it's got this nice green background, which says everything's OK. Right, so as you've seen, these type providers, they can do arbitrary computation at compile time. This may not seem like the most useful thing in the world. So in order to motivate a way in what it might be useful, we need sort of one concept which you may not have seen before, which will also justify why these things can return arbitrary types rather than just the type of types type. This is because we really, in F#, what you're doing with a type provider is you're typically generating both some types and some code for working with them. And we can't do that in this model because we're only filling out the right-hand side of a single definition. So instead, we use this trick called generic programming with universes, which you can see is sort of a dependently typed design pattern in some sense. And so if we want to do something that works at multiple different types, but maybe not every possible type, the first step is to define a data type that whose constructors represent the types that are in the universe that we care about. This is why it's called the universes. So here I'm designing a universe that contains natural numbers, lists of natural numbers, lists of lists of natural numbers, until you get sick to your stomach saying list of list of list of list. So we have 2 data constructors of this type U. The first is nat, and the second is list of some U. Then we define a function which maps this to actual Idris types. So interp takes a U and gives back a type. Interp of the code nat gives me back the actual type nat. Interp of list of some code t gives me back the actual type list of the interpretation of t. If I want to define a function that works for anything in that universe, I can then have the first argument be a code the second argument be an element of the interpretation, and in this case, we're going to return the same type. We could also return something else if we wanted. So in the first case, we check if our code was a NAT. And if our code was a NAT, then we know that the type of the second argument is actually going to be a NAT again. And so we can apply the successor constructor. This was called suck in Stephanie's talk last night. So we've added one to that argument. If it's a list, then we're going to want to add one to the elements of the list generically. So if that list happened to be the empty list, then we return the empty list again. If it's a list whose head is called x and whose tail is called x's, then we use our code t, sort of the inner code, to add one to whatever the x happened to be. And we use our code list of t to add one to the tail of x, or the tail, x's, whatever that happens to be. And so then we can see, sort of at the Idris REPL, that add one of the code list of nat gives us a function from lists of nat to lists of nat. Adding one to nat gives us a function from nat to nat. Adding one to list of nat, or adding one at list of nat to the list from 1 to 4 gives us back the list from 2 to 5, as expected. So what we're going to do for this SQLite type provider is design a code that's representing the types that we might have in our database schema, a type provider to parse the database schema and return the code representing it, and then have some generic functions for doing queries and building queries over these things. Okay, so I like demos. I like to live dangerously while doing talks. So we'll come to the type provider demo. Okay. So the first thing that we're going to do here is a little bit of Idris mumbo jumbo for telling how the generated C code should link to the SQLite API. But after that, we have this provider, which is providing some DB as the type DB of test.SQLite. And it's going to call this type provider get schemas of test.SQLite. And that run function is there simply because it's using a side effect management library, which needs me to call run to actually make the program go. So this database, test.SQLite, if we take a look at the schema, we can see that it's got two tables. It's got a table called talk, which contains titles, abstracts, and references to speakers. And it contains speakers who have names and bios. And note that bios are potentially nullable, the other columns are not. That'll come to be important later. If I want to look at the contents of speaker, it's got myself, another speaker, and lots of speaking. And as a very vain person, I gave myself a bio and nobody else. If I want to see what talks we have available, I first need to type correctly, which is a challenge to me today. Yeah. Yes. So we see that there's the talk that you're listening to right now, type providers and error reflection in Idris. There's monadic missile launching and an actuarial DSL. I figured these things might be of interest to functional programmers in New York. And then if I wanted to generate maybe a program for this conference, I'd want to do a join between those two tables. I'm sure you've all seen lots of SQL in your lives, and I don't need to bore you with it at the moment. It's much more fun to write it in Idris than it is in SQL anyway. So inside of Idris now, I can say that I've got a query, and the result of the query will have this schema. It's going to have a column name, which has type text, which is a SQLite type. And it has a bio, which is a nullable text. Remember that we left bio as nullable. And then it's selecting this particular schema from speaker, and then we have to say where one, because SQLite really doesn't have any notion of Booleans, so we're using ints. So I've got a little comment here to myself to remember to actually show that this code works. So we load it up. It takes a little bit of time to type check because it's actually going out and talking to the database. So I paste this here. So what I'm doing is unsafe perform IO of run of query of speakers, and we get back the same data that you saw in the underlying database. Sorry, I have an idea that this is at the bottom of the screen and therefore more difficult to see than it should be. So we're getting back that we got a string back in the first case. In the nullable case, we got a maybe type, so we have just and then my little bio there. And then the other two speakers, called another speaker and lots of speaking, don't have bios, as we would expect. Returning to the code here, we can also get the titles and abstract of talks the same way. And if we want to get a program, then we can take the Cartesian product of speaker and talk, restrict it to those cases where the column ID is equal to the column speaker. So ID is coming from speaker, and the speaker column is coming from talk. So it's a reference to it. And then we project out the columns that we actually care about. So this is like a little embedded language inside of Idris, which is kind of fun. And it's type safe, which is to say, if I thought that this should be called ID speaker for some reason, and then I try to load my file, it sits there and thinks for a while, and then it gives me back this atrocious error message. But nevertheless, my code didn't compile. If you'd like to look at the details, you can, but part of the point of the second part of the talk is going to be that you don't have to look at those details. Likewise, say I forgot that my bio column were nullable, and I deleted the fact that it was nullable. I try to load it. I get back another static error. Once again, not the prettiest in the world yet. Okay. So how does this work? Well, first off, we have a simple data type called SQLite type, which is codes representing individual things that can be there. This is maybe not the best type of codes you'd want in the world, because you can still say nullable of nullable of nullable of text. In practice, you'll never get that from a real database, so I didn't think it was worth the effort of ruling it out here in the type system, because it would make the slide a lot longer, but it could be done. Then I've got an interpretation function, just as we saw before, which interprets the type of codes as the Idris types of the values that correspond to them, which we'll be getting out of our database. The triple colon notation that you saw, annotating the types of the columns, is this type here. So it's an infix constructor triple colon, which takes a string as a column name and a code for a SQLite value type. A schema, which were these sort of lists of attributes, are basically just lists of attributes. And I could have really used list of attributes here, except I think that it's nicer sometimes to split off individual types for useful things. It can improve error messages and auto-completion and things like that. In Idris, if you call a type's constructors nil and double colon, then you can use list notation to build it, which is how we're able to have the sort of square brackets and comma notation for the schemas. Then a row can be defined as a type that depends on a particular schema. So here's where we get some more fun dependent types in here. So we see that the data type row is actually sort of a family of data types. So for every particular schema, there's a type of rows in that schema. So inside of the empty schema, we have the empty row, nil. And then inside of a schema that consists of some column name call and some code for a type t, extending some other schema s, we then have a row which consists of consing the interpretation of the code t onto a row of s. So if we have some schema that has name as text and age as int, then we could have a row in that schema might be the string David and the int 30 and then nil. And so these things sort of match up point by point. A database then, this is what the actual type provider is computing. It takes the name of the database file that was loaded, and note that it moves that up to the type level at the very end, and this is to prevent us from confusing the two things at compile time if we want to talk to two different databases. It doesn't make much sense to ask the database to join something with a table that is present in another database, so it's kind of nice to keep them separate here. And then it has a list of pairs of strings and schemas, which is to say table names and then the schema which is there. And so what the type provider actually is doing is it's just querying SQLite for this information, parsing it, and then constructing a perfectly ordinary data type. Queries are then represented using this AST here. So a query has a single constructor called select. Obviously, we could make this more complicated for a real example if we wanted to do sort of actual database crunching, but then again, we'd have slide fitting issues. And so it takes some database in some file name f, and the key here is that that's in curly braces. Curly braces says to Idris, please solve this for me. So just like in Haskell, as we saw in the previous slide, or a slide earlier, so we have these names t, s, and call down below. And just like in Haskell, we write them with lowercase, and this means that Idris will find the right values for us. So like in Haskell, you could say like list of A, it'll figure out what A is. Idris can do that typically. But in other cases, we don't want to write it with the lowercase, and we need to give it a little bit of a type annotation, so then we can sort of explicitly tell Idris that this argument is one you should figure out for me by sticking it in curly braces. So users will typically never have to write the value of db here, because it can be inferred from looking at the expected type. Then it takes a list of tables here, and that list of tables is what was constructed by either having a single table or having the Cartesian product of tables that we saw on the code. It then takes an expression, which is the selection, sort of what's being used to actually restrict the rows that we keep. It takes some schema S prime. So note that tables are in S, so that's a list of tables, and then it gives back like a particular schema that we get by taking their Cartesian product. And then what we get is S prime is the actual query, the actual result we want to get back out of our query. So that's that list of columns. And then we get a proof that this list of columns makes sense, right? That it's a subschema of the other one. So subschema is a data type which represents the fact that every column in one schema exists in another one, but not necessarily the other way around. And this auto keyword invokes Idris's proof search functionality to fill that out at compile time so that the user doesn't have to type it either. And what we get back is a query in that database and in the resulting restricted schema. We can get that nice syntax with a simple parser extension. This is valid Idris syntax. I say that syntax select of schema from tables where expression is then an application of that select constructor up above to tables, expr, and schema, which are the explicit arguments expected by the select constructor. And then this type provider is talking to SQLite, querying to get the schemas, parsing the data definition language, and returning an instance of that db type, which we saw earlier. Now, this is all great, but remember those error messages? They were pretty horrible. Like here's an example of one of them where I've actually cleaned up the formatting to make it more readable, and I still think that it's not a very good error message. It's got a couple of problems. The first one is that it's saying can't solve goal, and this is actually a new feature, a somewhat newer feature. Before that, it would have been something even crazier. So what it's saying is I couldn't find a proof that the schema append of ID, name, and bio, and title and abstract of speaker contains a column called speaker ID with type integer. So we have this sort of unapplied function inside the error message, and the compiler can't know which things it should reduce inside of errors. If you're in the Emacs mode, you can right-click and say, like, reduce this term, and it'll do it. But still, I think that really, if we expect people who aren't familiar with the internal implementations of that embedded query language and the type provider to use this, then we really need to provide a better interface also for our error messages. This is the error message that I really like to present, right? I'd like to say that the column speaker ID was not found with the type integer in this schema right here, which is the result of doing that application. Does everybody agree that this would be a better error message? Great, I'll show you how to get there. So a little bit about the internals of Idris is necessary to sort of understand how this works. So inside of the Idris compiler, the high-level language that you program in is first translated to a core language, which is much, much simpler. It's actually even simpler than the one you saw at the talk last night, because it doesn't have a lot of the primitives. And then after that, once we've type-checked that, it's much easier to type-check a simple language and be confident that our type checker is actually doing the right thing. We can then compile that, and it dumps out C code or one of the other backends. But there's another feature that we have in Idris, which is called reflection. And what reflection does is it takes the compiler's internal data structures that represent this core language, and it moves them up to an actual Idris data type representing the core language. And so we have sort of two operations. There's reflection, where we're pulling up our representation of a core term, and then we have reification, which is where we take a reflected term and then turn it into an actual term, and then the compiler can go onward with it if it type checks correctly. So we don't lose any type safety with this. It's a compile time only metaprogramming feature. And this is a feature that was already in Idris before I started hacking on it. So it's sort of traditionally these kinds of reflection features have two main uses. One of them is doing custom proof tactics. So you can say, if you have some sort of complicated thing you'd like it to prove, then you can create a little mechanism for doing that. But also it's nice for decision procedures for solving implicit arguments. So before you saw that we could write auto. Well, auto doesn't work in every case. Sometimes if you want users to not have to deal with something, you have to automate it. And reflection is a nice way to do that, because you can pattern match on the reflected representation of the goal that you're wanting to solve. What we're going to use it for here is rewriting error messages. So error reflection is a small extension to the built-in reflection mechanism, which takes compiler error messages and lifts them up to an Idris data type. So here's an example of an error message that happens when you try to use a bool where the compiler is expecting a nat. This is a pretty big, ugly data type. It'll get better. But what it's saying is that it can't unify the type constructor of nat with the type constructor of bool. So we have our nat and we have our bool there. And then it's got some internal message stuff and some internal context things which aren't being used here. By pattern matching on these reflected error message, Idris code can generate new error messages that are sort of domain specific. But before we get to that, there's a nicer syntax we can use. So if we have the list of some t and we want to take the reflection of that, then we get the application of the type constructor of list inside of the namespace prelude.list with this type to type, and this is for list of something, right? I mean, if you have some big complicated goal like this schema has this column, then you're totally in trouble. So we have I love Lisp, so I figured I'd steal some good ideas from Lisp, and in what's going on here? There we go. And so I can represent the exact same thing that we had above by writing backtick of list of tilde of t. So the tilde here is working kind of like a comma would in traditional Lisps, or just like the tilde does in Clojure, if anybody here is using that. And so the reason why this works is that the Idris compiler already knows how to translate high-level Idris code to the core language. So it just does that for us, and then we ask for the reflected representation rather than using it. So now that you understand what that crazy backtick notation means, here's a version of the same file that we just saw where I've introduced a couple of mistakes. And these are the same mistakes that you saw before. So we've got, when elaborating the argument, okay, blah, 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 can't solve this goal, So what I'm going to do is open up a file called error handlers. And so what error handlers contains is a couple of functions for rewriting error messages. So the first thing is a little utility function called getAtters, and what getAtters does is it takes a reflected representation of a schema, or of a list of attributes, basically, and it converts it to a nicely formatted error message part. So we have this type error report part. That's the reason why we're not returning strings as error messages here is we'd like to be able to use the Idris pretty printer to print terms inside of our errors and get things like nice semantic highlighting. So we getAtters of the reflected attribute a : B. We take out the A and the B and stick them with a text : before, and subreport causes something to be rendered as like a little indented column kind of thing. And then we have a couple of other things where we grab the contents of cons and then the contents of an application of the append function, which is what we saw before, so that we don't actually have to evaluate and normalize that. The next step is this hasCall error is a rewriter for one of our goals, which is the one that happened when we spelled the column name wrong. And what that does is it takes the error, the reflected error, can't solve this goal of has column and then some schema and then what we want. So note that the schema and what we want are escaped. And because we're in a pattern context, they become pattern variables as opposed to being things that we're constructing using the backtick. Is that a question? It's escaping the quotation. So it's like comma in Lisp. And so what we have here is we can pull out this getWant. So what this is used is to actually get an error message, a little sub bit of the error message based on the type that we wanted. That's saying the column of C was not found with the type typ. And it's wrapping this all up inside of a maybe. This funky notation with the square brackets and the pipes, yeah. Okay, the notation with the square brackets and the pipes is something called an idiom bracket, which is a notation for working with applicatives, kind of like do notation is for monads. If you don't know what those are, you can think of it as taking this function append, which is the plus plus here, and making it work on maybes of things, handling nothing in the appropriate manner. The percent language error reflection up at the top turns on this error reflection feature, which will, because it's off by default, it doesn't let you rewrite errors because I considered it an experimental thing, and it's exactly like a language pragma in GHC. Yeah, thanks. Okay. And then if the error that we got is not the kind of error that we know how to rewrite, we just return nothing. The other kind of error message that we saw was the one that this schema is not a subschema of the other one, which is to say that the schema we're asked for is not something that we can get out of the schema of our query. So in that case, we've got subschema of S1 and S2 is unsolvable. And then we say that S1 is a bad schema using that getAtters function, which renders it as a nice little table. And then we say that we expected it to be a subschema of getAtters of S2. And then we have the same thing here written without error reflection just to show that it's horrible. Or without quasi-quotation, just to show that it's kind of horrible. So, returning to my error test, I can then come up here and uncomment these conveniently placed lines. And what error handlers call OK has call error means is it means to take the constructor, type constructor, or function named call, and its argument named OK. Because we have dependent types, the dependent function type allows you to name one of your arguments, so we piggyback on that feature here. So OK is the thing that would be solved by the proof search to figure out that this column actually exists. And then we use the function hasCallError to rewrite error messages in there. And then you can give a comma-separated list of error rewriters. The reason for restricting it to one little scope like this is to prevent false positives, because there's nothing worse than getting a domain-specific error message for a domain you're not working in. And likewise, the not subschema error handler is associated with the other error that we had. Reloading the buffer, we get back much nicer error messages. So in the case of select, we get that name and bio is not a subschema of the one which contains ID, name, and bio, where bio is a nullable text. I think this would make it much easier to find the bug. Likewise, we have the column speaker ID was not found with the type integer in the schema, and then this table thing, which is the result of that getAtters function. I hope you believe that this is a much better error message. And we could do a lot more work here as well. So if I wanted to have much longer error rewriter functions, then I could do things like actually find the column which does not match here and say this one here doesn't match in this particular way, and show a little diff if I wanted to. These are arbitrary Idris functions, so you can do basically whatever you want. Okay, so as a little conclusion, type providers, inspired by the awesome stuff they have in F#, let Idris code generate types based on I/O actions, and these types can be about something in the real world around your code, right? Our type theory is no longer a beautiful, pure jewel of excellence hiding away from all the dirt surrounding it. We can sort of push that dirt in and integrate it into our program. When things go wrong, error reflection can be used to actually explain how and why it went wrong so that somebody has a hope of fixing it. So if you'd like to get a hold of me to learn more about this, say I'm doing it wrong, something like that, you can find a webpage up here or email me. If this seems like it might be fun to learn Idris, which is a dependently typed language for actually writing programs, you can check out idrislang.org, #Idris on Freenode. The wiki on GitHub is kind of hard to find, but it has lots of good information as well, especially help installing it. And the Type Theory podcast episode 2 has an interview with Edwin Brady on how Idris is put together internally. So if you would like to hear how another dependently typed language is implemented, that might be a good place to go. Thank you very much. Yeah. Questions? Kenny. Yeah. Yeah, so the question is if I can explain a little bit more about how the quasi-quoting works for pattern matches. So what happens when you see a quasi-quote is that the Idris elaborator, which is the part that translates the high-level language to the low-level core language, is run. And what the elaborator then does is it generates that data type. And if we're doing anything that we escape is escaped using the rules of whatever context we're in. So for on the right-hand side, then it'll look for data for a variable called, like for in the example of the list T, it'll look for something with the type T with the type of reflected term, and it'll try to fill it in using the normal rules of variable resolution. On the left-hand side of a definition, a variable that's left in a pattern is just a pattern variable. So it uses the exact same rules of patterns. There's a little bit of fancy stuff going on for universal patterns to make those work right and things like that. But yeah. 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 So the question was that the assumption is that auto is using a tactic to solve things, and if the solution isn't very good, can you do something else? And the answer is yes. So there's a built-in proof search tactic, which is what auto calls. If you don't like that, then you can write your own tactic and have that run in your data type to solve implicit arguments or in your function. And if you don't like what the library author has chosen, then you can always say, make this argument be exactly this value rather than using a tactic to solve it as a user. Okay. Do I have time for one more if there's? Okay. Is there one more? I suppose not. Thank you.